Welcome to the deep dive. Today we're tackling, well, a really huge problem at the heart of modern physics. It's this conflict, this kind of dark cloud that's been hanging over physics for, what, more than 50 years now?
Oh, easily. It's arguably the biggest challenge. We're diving into the quest for what you might call the ultimate theory, something that finally connects the dots between the universe's biggest scales and its tiniest components.
Because right now we have these two incredible theories, right? General relativity and quantum mechanics. Both work amazingly well in their own areas.
Amazingly well is an understatement. General relativity, Einstein's masterpiece, gives us this beautiful picture of gravity, space, and time. It governs stars, galaxies, the expansion of the whole universe, the really big picture.
And then you've got quantum mechanics, which is, well, equally successful, but frankly much, much weirder. It's our rule book for the ultra-small. Molecules, atoms, subatomic particles, quarks, electrons, that whole world.
The deep paradox, the core of the problem, is that these two pillars, both proven right time and time again in experiments, just don't play nice together. They're fundamentally incompatible.
And that incompatibility really blows up when you try to describe situations that are both incredibly small and incredibly massive or energetic.
Exactly the extreme cases. Think about the very center of a black hole. You have immense mass crushed down into, well, theoretically, an infinitely small point.
Or rewind all the way back to the Big Bang itself, the entire observable universe squeezed into a space smaller than an atom, but with unimaginable energy.
Right. And when physicists try to use both general relativity and quantum mechanics to figure out what's happening in those extreme scenarios, the math just completely breaks down.
It gives nonsense answers, like infinities.
Precisely. Meaningless infinities, mathematical singularities. The equations basically throw their hands up and say error. So our mission today is to really unpack these two theories, see why they clash so violently, and then explore how this really radical idea, string theory, proposes to, well, maybe finally bridge that gap.
Okay, let's start with the grand scale. General relativity. To really get Einstein's leap, we need to remember what he was fixing, right? Newton's gravity.
Yeah, Newton's picture was brilliant for its time, but it had this, well, spooky aspect. Gravity was an instantaneous force acting across any distance. If the sun just vanished, poof.
Earth would instantly feel it, according to Newton, fly off into space right away.
But Einstein, with his earlier theory, special relativity, had already established a universal speed limit, the speed of light. Nothing, absolutely nothing can travel faster. No signal, no influence.
So Newton's instant gravity had to be wrong. Information about the sun vanishing couldn't possibly reach Earth instantly.
Exactly. It took Einstein years, but his solution in 1915, general relativity, was revolutionary. Gravity isn't some mysterious force reaching across space. It's the result of mass and energy warping the fabric of space-time itself.
So space and time aren't just a static backdrop, they're an active player.
They're the medium. Mass and energy tell space-time how to curve, and space-time in turn tells mass and energy how to move. That curvature is what we experience as gravity. And crucially, these warps, these ripples in space-time, travel at the speed of light.
Okay, the famous analogy here is the bowling ball on the rubber sheet, right? Helps to picture it.
It does. It's a classic for a reason. The heavy bowling balls say the sun makes a big dent in the rubber sheet, which is standing in for space-time.
And a smaller ball, like the Earth, rolling nearby, follows the curve caused by the bowling ball. That path looks like an orbit.
Yep. It gives you the basic idea of mass causing curvature and curvature dictating motion. But we have to be careful with it. The analogy isn't perfect.
Right. What are the key things it gets wrong?
Well, two big ones. First, in the analogy, the bowling ball sinks down because Earth's gravity is pulling it down, right? An external force. In general relativity, there's no external down. The sun's mass itself causes the warp. The curvature is the gravity. It's intrinsic.
Okay, that makes sense. No outside force needed. What's the second issue?
The rubber sheet is two-dimensional. Reality, as we experience it, has three spatial dimensions plus time. So 4 dimensions total. General relativity describes warping in all those dimensions, which is much harder to visualize than a simple dip in a 2D sheet.
Right, so it's more complex, a 4-dimensional warp, as Wheeler famously put it. Mass grips space, space grips mass.
By telling it how to curve, space grips mass by telling it how to move.
Exactly.
It's a dynamic interplay.
Now, if space is warped, what about time? You mentioned special relativity earlier, and that theory already messed with our intuitive ideas about time and simultaneity.
Oh, absolutely. Special relativity's core idea is that the speed of light in a vacuum is constant for everyone, no matter how fast they're moving. That simple fact has profound consequences.
It forces space and time to become relative, flexible things.
It does. Take the time dilation example. Slim in his Trans Am doing 120 miles per hour, Jim standing by the road timing him.
If Jim measures, say, 30 seconds passing on his stopwatch,
Slim's clock, inside the moving car, will have ticked just a tiny, tiny bit slower.
Yeah.
For 30 seconds on Jim's clock, Slim might measure 29.99, a whole lot of nines. 52 seconds.
the difference is incredibly small at everyday speeds, like 120 mil per hour, basically unnoticeable.
Completely unnoticeable in daily life. That's why our intuition doesn't grasp it. But the effect is real, and it becomes significant as you approach the speed of light. The faster you move through space, the slower you move through time relative to someone stationary.
And this kills the idea of a universal now, doesn't it? The relativity of simultaneity.
It totally does. The classic thought experiment is the peace treaty signed on a moving train. Presidents at each end, light bulb exactly in the middle, flashes.
For people on the train, the light reaches both presidents at the same instant. Simultaneous signing.
Yep. But for someone watching from the station platform, the train is moving. The president at the front is moving towards the light pulse, while the president at the back is moving away from it.
And since the speed of light is constant for the platform observer too?
The light must reach the front president first. So for the platform observer, the signing is not simultaneous. The front president signs before the back one.
And neither viewpoint is more correct than the other.
Nope. Both are equally valid frames of reference. There's no absolute simultaneity. What's simultaneous for one observer isn't necessarily simultaneous for another moving relative to them. General relativity then adds another layer of gravity itself, warps time. Clocks tick slower, closer to a massive object. Hashtag 1.2, the standard model and arbitrary ingredients.
Okay, so GR gives us this amazing dynamic picture of space-time. Now what about the stuff in space-time? The particles. That's the domain of the standard model.
Right. The standard model of particle physics is, well, the other spectacularly successful theory. It describes all the known fundamental particles and how they interact via 3 of the 4 fundamental forces.
And basically everything we see, touch, interact with, it's all made from just a few basic building blocks, isn't it?
It's remarkably economical at its core. Ordinary matter is just electrons, up quarks, and down quarks. Protons and neutrons and atoms are combinations of ups and downs. Add electrons orbiting, and you've got atoms, molecules, chemistry, us.
But when physicists smash particles together in giant accelerator, they find a lot more than just those 3. It gets complicated fast.
Oh, it's a whole particle zoo. Besides the up and down quarks, there are 4 heavier quarks. Charm, strange, top, and bottom, and the electron has 2 heavier, unstable cousins, the muon and the tau. Plus, there are 3 types of incredibly elusive particles called neutrinos.
So 12 matter particles in total, plus their antimatter counterparts. Okay.
And here's where the first big headache for the standard model comes in. These particles seem to fall neatly into 3 groups, or families.
Families. How so?
Each family is like a heavier repeat of the previous one. The first family is the electron, its neutrino, the up quark, and the down quark, the stable stuff. The second family has the muon, its neutrino, the charm quark, and the strange quark. They're identical to the first family particles in terms of charge and how they interact, but they're much heavier.
And the third family is the tau, its neutrino, the top quark, and the bottom quark, even heavier still.
Exactly. The tau, for instance, is like a super heavy electron, about 3,520 times its mass. The top quark is monstrously heavy compared to the up quark, over 40,000 times heavier.
Okay, so the big question is, why? Why 3 families? Why this bizarre, seemingly random spread of masses?
And the standard model just shrugs. It doesn't explain it. These masses, along with about 17 other numbers like the strength of forces or the electron's charge, have to be measured in experiments and then plugged into the equations by hand.
They're arbitrary inputs. The theory doesn't predict them.
Not from first principles, no. It's like having a brilliant recipe book that tells you exactly how to combine ingredients, but it has no idea why you have those specific ingredients or why they weigh what they do. That feels incomplete. Unsettling for physicists seeking a deeper understanding.
That lack of explanation for the fundamental ingredients is a major driver for seeking a unified theory. And there's another huge issue, right? Gravity.
Yes, gravity.
Yeah.
The elephant not in the room as far as the standard model is concerned. It describes the strong, weak, and electromagnetic forces beautifully, but it completely leaves out gravity.
And not only is gravity left out, but when you compare it to the other forces, it's just incredibly weak.
It's absurdly feeble. Take 2 electrons. The electromagnetic force pushing them apart is about 10 times stronger. That's a 1 followed by 42 zeros. than the gravitational force pulling them together.
1042 times.
Oh.
It's hard to even comprehend. So why does gravity seem so dominant on, human scales or planetary scales?
It's because gravity is always attractive, and it adds up over large scales. Mass attracts mass. The trillions upon trillions of atoms in the Earth all pull together gravitationally. Electromagnetic forces, on the other hand, involve positive and negative charges, which tend to cancel each other out, making large objects electrically neutral overall.
So gravity wins on the macro scale because it's a team player, always adding up, while electromagnetism is full of internal cancellations.
Pretty much. But fundamentally, particle to particle, gravity is just this incredibly faint whisper compared to the other forces. And that extreme weakness makes it incredibly hard to study its quantum nature, to find the hypothetical graviton particle that would carry the gravitational force like the photon carries electromagnetism. It's the outcast force. All right, so to really understand the clash with general relativity's smooth space-time, we need to dive into the weirdness of quantum mechanics. Its origins go back to trying to understand something seemingly simple: how hot objects glow.
Right, blackbody radiation. Classical physics, based on continuous waves of energy, made a prediction that was spectacularly
Totally wrong. It predicted that a hot object should emit infinite energy, especially at higher frequencies like ultraviolet light, the ultraviolet catastrophe. Clearly something was missing.
And Max Planck came along with a radical idea. Energy isn't continuous, it comes in chunks. Quanta.
Exactly. He proposed that energy could only be emitted or absorbed in discrete packets or lumps, and the size of the energy lump was proportional to the frequency of the radiation. Higher frequency, bigger energy packet. He introduced a fundamental constant, now called Planck's constant, that set the scale for this lumpiness.
It's like energy comes in specific coin denominations, and you can't deal in fractions of a cent.
That's a great way to put it. If the denomination required for a very high-frequency wave was too large compared to the available thermal energy, that wave just couldn't be produced. This instantly solved the ultraviolet catastrophe and matched experimental data perfectly. Energy is fundamentally granular.
And Einstein took this idea of energy packets even further a few years later with the photoelectric effect.
He did. The puzzle was why, when you shine light on a metal surface, electrons get kicked off. Classically, you'd think making the light brighter, increasing its intensity, should make the electrons fly off faster, with more energy.
But that's not what happens. Brighter light just knocks off more electrons. To make them fly off faster, you need to change the light's color specifically, increase its frequency.
Right. Einstein explained this by saying light itself isn't just a wave, it's also a stream of these energy packets, which he called photons. Each photon carries an energy proportional to its frequency, its color.
So a photon of blue light carries more energy than a photon of red light.
Exactly. To knock an electron off the metal requires a certain minimum energy, like a cover charge. If a single photon hits with enough energy, high enough frequency, it kicks the electron out. Any extra energy the photon had becomes the electron's kinetic energy, how fast it moves.
And increasing the intensity.
That just means you're sending more photons per second. More photons hitting means more electrons getting knocked out, but each electron still only gets energy from one photon collision, so their individual speeds don't change unless you change the frequency, the energy per photon. Hashtag 2.2 wave particle duality and uncertainty.
This photon idea solidifies the particle nature of light, but quantum mechanics immediately throws a curveball, wave particle duality. The double slit experiment is the classic mind-bending example.
Oh, it's the absolute core of quantum weirdness. If you fire particles, photons, electrons, even atoms, one by one, towards a barrier with two narrow slits in it.
You'd expect them to act like tiny bullets, right? Just pile up in two distinct bands on the detector screen behind the slits.
That's the classical intuition. But it's completely wrong. What you actually see emerge, even firing them one at a time, is an interference pattern. Alternating bright and dark stripes.
Which is the unmistakable signature of waves interfering, peaks adding up to make bright spots, peaks meeting troughs to cancel out and make dark spots.
Precisely. It's as if each single particle somehow goes through both slits simultaneously as a wave, interferes with itself, and then decides where to land on the screen as a particle.
And the truly bizarre part is that if you close one slit, the pattern changes completely. Spots that were dark when both slits were open can suddenly become bright when only one is open.
It defies common sense.
Yeah.
How does a particle going through, say, the left slit know whether the right slit is open or closed? The only way to make sense of it mathematically is to accept this wave-like behavior.
Richard Feynman had an even wilder way to think about this, didn't he? The path integral idea.
Yeah, Feynman's picture is radical. He said, forget trying to pinpoint which path the particle takes. To calculate the probability of an electron going from point A to point B, you have to assume it simultaneously considers every single possible path connecting them.
Every path. Like even ones that loop around the moon or zip out to another galaxy and back.
Yes. Every conceivable path, no matter how crazy. You assign a mathematical value to each path, and then you sum them all up. Miraculously, for large objects, all the wildly different paths cancel each other out mathematically, leaving just the one classical trajectory we expect.
But for tiny quantum particles,
many different paths contribute significantly, and their combined probabilities lead precisely to the wave-like interference patterns we observe. It tells us the microscopic world is fundamentally probabilistic, not deterministic. We can only predict the odds of where a particle might end up.
Okay, this inherent fuzziness, this probability, it leads directly to Heisenberg's uncertainty principle, right? And that's where the real conflict with smooth space-time starts.
Exactly. The uncertainty principle isn't just about limitations on measurement. It's about a fundamental property of nature. It states you can't simultaneously know certain pairs of properties, like a particle's exact position and its exact momentum, with perfect accuracy. The more precisely you know one, the less precisely you know the other.
And there's an energy time version of this too.
Yes, and that's crucial. It implies that energy conservation can be briefly violated as long as it's paid back quickly. This means even supposedly empty space, the vacuum, isn't truly empty.
It's buzzing with activity.
It's a teeming, roiling frenzy, as Brian Greene puts it. Virtual particles, antiparticle pairs are constantly popping into existence, borrowing a tiny bit of energy, and then annihilating each other almost instantly, paying the energy back. It's like quantum accounting, tiny short-term loans are allowed.
And this frenzy gets worse at smaller scales.
Much worse. The smaller the region of space and the shorter the time scale you look at, the wilder the energy fluctuations become. The vacuum becomes increasingly agitated, a chaotic foam of virtual particles and fluctuating energy fields.
And general relativity, with its picture of a smooth, gently curving space-time, it just can't handle that kind of microscopic chaos.
It completely breaks down. GR assumes space-time is smooth. Quantum mechanics insists that on tiny scales, it's violently turbulent. When you try to apply GR's equations in that quantum foam, especially to calculate the effects of gravity at those scales, the graviton interacting with virtual particles, the infinities pop up again. The math implodes. Smoothness versus chaos, they fundamentally disagree on the nature of reality at its smallest level.
So this is the impasse. GR and QM clash violently at the intersection of the very small and the very energetic. Enter string theory. What's the core idea here? It's a pretty radical departure, isn't it?
It's a fundamental shift in perspective. For centuries, we've thought of the basic building blocks of matter as point particles, dimensionless dots. String theory says, no, that's just how they look from far away.
If we could zoom in, like way
Beyond anything we can currently probe, yes. String theory proposes that if you could look closely enough, you'd see that what we call a particle, an electron, a quark, a photon, isn't a point at all. It's actually a tiny, vibrating, one-dimensional loop or filament, a string.
So everything is made of tiny vibrating strings. That's the central hypothesis.
That's the core idea. These strings are incredibly small, maybe around the Planck length, which is about 1035 meters. Absolutely minuscule.
Okay, tiny strings. How does replacing points with strings help solve those big problems we talked about, the arbitrary masses in the standard model and the clash with gravity?
Well, think about a violin string. It can vibrate in different ways, right? Different patterns of vibration produce different musical notes.
Higher notes, lower notes, harmonics, yeah.
String theory proposes something similar for these fundamental strings. The different ways a string can vibrate its resonant patterns correspond to different particles. One vibration pattern might make the string appear as an electron. A different vibration pattern would make it appear as a quark. Another, a photon.
So the particle properties like mass and charge aren't arbitrary inputs anymore. They're determined by the string's vibration, like the music it's playing.
Exactly. The string's vibrational energy determines the particle's mass via E mc to the on. Its specific pattern of vibration determines its force charges, like electric charge. Suddenly, there's a framework to explain why particles have the properties they do. It's all down to the notes the strings can play.
That sounds much more elegant than just plugging in numbers. And what about gravity? The outcast force?
This is one of the most beautiful parts. Among the possible vibration patterns of the string, there's one specific pattern that has exactly the properties required for the graviton, the hypothetical quantum particle of gravity.
Right.
0 mass, 2 units of spin. It just naturally falls out of the mathematics.
So string theory doesn't just allow for gravity, it requires it. Gravity is automatically included in the quantum picture.
Precisely. It's the first theory that seems to seamlessly weave general relativity's gravity into the quantum framework right from the start. It's not an add-on, it's an essential part of the structure. Hashtag tag 3.2, resolving the incompatibility.
Okay, that's conceptually huge. But does it actually solve the mathematical breakdown? Does it get rid of those infinities that plague quantum gravity calculations with point particles?
Yes, and it does it in a really clever way that stems directly from strings having size, unlike points. Think about how point particles interact. The interaction happens at a single, infinitely small point in space-time.
And that's where things go wrong. The infinities crop up at that point.
Right. All the problematic physics gets concentrated at that infinitesimal point. But strings aren't points. They are tiny, extended loops. When two strings interact, they don't collide at a single point.
How do they interact then?
As strings move through time, they trace out a two-dimensional surface in space-time. Think of it like the timeline of the loop. We call this the world sheet. When two strings collide and interact, they merge and split. And the interaction point isn't a point anymore. It's smoothed out over a small region of this world sheet.
So the interaction is smeared out because the strings themselves aren't infinitely small points.
Exactly. That smearing effectively dilutes the interaction. It avoids concentrating all the force at an infinitely small location. This smoothing is enough to tame the infinities that wreck the point particle calculations for quantum gravity. The math becomes finite and well-behaved.
So the extended nature of the string is the key to avoiding the mathematical catastrophes. Does it also affect how we think about distance itself?
It fundamentally does. String theory seems to imply there's a minimum meaningful distance scale in the universe, the Planck length, roughly the size of the strings themselves.
You can't measure anything smaller than a string because your probe is a string.
Essentially, yes. It's like trying to measure the grooves on a record using the needle itself. You can't resolve details smaller than the probe. This suggests we can't actually probe the sub-Planck length realm where those violent quantum fluctuations were supposed to be destroying space-time, according to the old theories.
So the theory naturally prevents us from looking where the problems were. It imposes a fundamental resolution limit on reality.
That seems to be the implication. Those ultra-short distances where the quantum phone was supposedly raging out of control might simply be inaccessible, or perhaps meaningless, within the framework of string theory. The theory smooths out the physics and sets a limit on how closely we can examine it. Hashtag 3.3 dimensions, supersymmetry, and dualities.
Okay, vibrating strings, solving infinities, and unifying forces sounds amazing. But there's a catch, isn't there? A rather big one involving dimensions.
Ah, yes, the dimensions. For string theory's mathematics to be consistent specifically, for quantum probabilities to behave sensibly and always add up to 1, the theory doesn't work in our familiar 3 spatial dimensions plus 1 time dimension.
How many does it need?
It requires a total of 10 space-time dimensions, 1 dimension of time and 9 dimensions of space.
9 dimensions of space,
Yeah.
but we only see 3. Where are the other 6?
This is where an old idea by Kaluza and Klein gets repurposed and expanded. The idea is that the extra dimensions could be spatial dimensions that are curled up or compactified to an incredibly tiny size.
The garden hose analogy, right? From far away, it looks like a 1D line, but up close, you see the 2D circular dimension around its circumference.
Exactly. So the idea is that at every point in our familiar 3 large dimensions, there are 6 additional spatial dimensions curled up into some tiny complex shape. They're so small, perhaps smaller than 1017 meters, way beyond what our experiments can resolve, that we simply don't perceive them directly.
And the shape of these curled up dimensions matters. It's not just any tiny shape.
Oh, it matters enormously.
Right.
For the theory to work and match observations, these 6 dimensions must be curled up into very specific kinds of mathematical shapes called Calabi-Yau manifolds. They're incredibly complex geometrical structures.
Calabi-Yau manifolds, and their geometry affects the physics we see.
Profoundly. The precise shape, the number of holes or handles in the specific Calabi-Yau manifold that describes our universe actually dictates the fundamental physics we observe in our large dimensions. For example, the number of holes in the Calabi-Yau shape is theorized to determine the number of families of fundamental particles we see in the standard model.
So if the shape has 3 holes, that could explain why we have exactly 3 families of quarks and leptons.
That's the hope. It would turn the arbitrary family structure of the standard model into a consequence of the geometry of hidden dimensions. The shape dictates the particle types, and potentially even their masses and force strengths. Physics becomes geometry.
Wow, okay, that's wild. Besides extra dimensions, there's another major requirement, right? Supersymmetry. SUSY.
Yes, supersymmetry is deeply woven into the mathematical fabric of string theory. It's a very high degree of symmetry that the theory seems to require for consistency.
And what does supersymmetry predict?
It predicts that every known fundamental particle should have a superpartner particle. These superpartners have the same mass and charge as their regular counterparts, but differ by half a unit of spin. So every fermion, like electrons, quarks, should have a boson superpartner, electrons, quarks, and every boson, like photons, gluons, should have a fermion superpartner, photinos, gluinos.
But we haven't found any of these superpartners. Selectrons, squarks, none of them.
No, not yet. If they exist, they must be much heavier than their standard model partners. Otherwise, we would likely have produced them in particle accelerators already. This is a major test for string theory, finding these particles.
So why is 6USY so important for the theory if we haven't seen its predictions yet? Does it help with anything else?
It does something remarkable regarding the fundamental forces. Remember how we said gravity is the outcast, much weaker than the others? Well, the strengths of the other three forces, strong, weak, electromagnetic, also change with energy. In the standard model alone, they get closer at very high energies, but don't quite meet at a single point.
They almost unify but miss.
Exactly. But if you include the effects of all the predicted superpartners and their quantum fluctuations, their contributions slightly alter how the force strengths run with energy. And with USY included, the calculations show the three non-gravitational forces converge perfectly, meeting at a single strength at an extremely high energy scale.
So 6USY predicts force unification. It makes the picture tidier.
It strongly suggests it, yes. It provides a mechanism for the grand unification that physicists have sought for decades. It makes the theoretical structure much more compelling, even if we haven't found the particles yet.
The theory just keeps getting stranger and more elegant. What about these dualities, like T-duality?
Dualities are some of the most profound and mind-bending aspects of string theory. T-duality relates to the size of those curled-up dimensions. It says something absolutely astonishing.
Hold on.
Imagine one of those extra dimensions is curled up into a simple circle of radius r. T-duality claims that the physics described by string theory in this universe is exactly identical to the physics in a universe where that dimension is curled up into a circle with radius other $$ in fundamental units.
Wait. A universe with a large radius r dimension is physically indistinguishable from one with a tiny radius $r. How can that be? Geometrically, they're totally different.
Geometrically, yes. Physically, no. It comes down to two ways strings can carry energy in a curled-up dimension. They can have winding modes wrapping around the circle like a rubber band, which costs more energy if the circle is large. Or they can have vibration modes vibrating within the dimension, which costs more energy if the circle is small, less room to vibrate.
Okay. Winding energy for large r, vibrational energy for small $.
T-duality shows that the spectrum of possible winding energies in the large R universe exactly matches the spectrum of possible vibration energies in the small $ universe, and vice versa. So any physical measurement you make, any experiment you perform, will give identical results in both scenarios. You fundamentally cannot tell the difference between radius r and radius 1 around.
That's deeply weird. It implies size itself isn't absolute at the quantum level.
It suggests a fundamental minimum length scale, related to the Planck length, below which the concept of smaller actually becomes equivalent to larger in this reciprocal sense. It's a cosmic mirror.
And this has implications for the very beginning of the universe, the Big Bang singularity.
Potentially huge implications. If the universe was contracting, heading towards the Big Bang singularity zero size, T-duality suggests something remarkable might happen. As the radius r shrinks past the Planck length, the physics would become indistinguishable from a universe whose radius 1 $. Is starting to increase.
So instead of crushing down to an infinitely dense point, the universe effectively bounces. The crunch is replaced by a bounce at the Planck scale because shrinking further is physically the same as expanding.
That's the tantalizing possibility offered by T-duality. It might provide a way to resolve the singularity problem at the heart of the Big Bang, suggesting the universe didn't begin from an infinitely small point, but perhaps transition from a contracting phase to an expanding one. #3.4 black holes in string theory.
Okay, resolving the Big Bang singularity is huge. What about the other extreme gravitational objects, black holes? They're the ultimate test bed for gravity and quantum mechanics meeting.
Absolutely. And black holes presented their own deep mysteries that hinted at quantum effects long before string theory. There's this weird observation, the no-hair theorem.
Meaning black holes are simple.
Surprisingly simple from the outside. The theorem states that an isolated black hole is completely characterized by just three properties: its mass, its electric charge, and its spin, angular momentum. Everything else about what fell in is lost.
Mass, charge, spin.
Yeah, hang on. Those are the exact same properties that define fundamental particles in the Standard Model.
Exactly. It was a very suggestive clue that maybe black holes weren't just collapsed stars, but had some connection to fundamental physics, bridging the macro gravity and micro particles.
Then came the ideas about black hole entropy, right, disorder.
Yes, Jacob Bekenstein made the bold proposal that black holes must possess entropy, a measure of internal disorder or hidden information, challenging the no-hair idea slightly. If things fall in, their information can't just vanish, maybe it's stored somehow. He even suggested the entropy was proportional to the surface area of the black hole's event horizon.
Proportional to the area, not the volume. That's weird for entropy. Usually it scales with volume.
Very weird. But Stephen Hawking provided strong theoretical backing when he showed, using quantum mechanics near the event horizon, that black holes should actually radiate heat very slowly, Hawking radiation. If they have a temperature, they must have entropy. And his calculation confirmed Bekenstein's idea. The entropy was proportional to the horizon area. But why? What microscopic constituents inside the black hole were being counted to give that specific area-based entropy? Classical GR says there's just a singularity inside.
That was the puzzle for decades.
Yeah.
What are the atoms of black hole entropy? And this is where string theory scored arguably its most stunning quantitative success.
How so?
In the mid-90s, using the advanced machinery of string theory, including not just strings but higher dimensional objects called D-branes, and special BPS states physicists Andrew Strominger and Kamran Vafa managed to build a theoretical model of a specific type of black hole purely from stringy ingredients.
They constructed a black hole from the bottom up using strings and branes.
Yes, for a certain class of extremal black holes. They could then use the rules of string theory and statistical mechanics to count the number of possible ways those underlying strings and branes could be arranged internally while still producing the same overall mass, charge, and spin for the black hole, basically, counting its possible microscopic states, its microstates.
And what did that calculation give for the entropy?
It precisely matched the Bekenstein-Hawking formula based on the black hole's surface area.
Yeah.
Exactly. Number for number.
Wow. So string theory could actually count the microscopic states and reproduce the mysterious area law.
It was a landmark achievement. It showed that string theory had the mathematical power to delve into the quantum structure of these extreme gravitational objects and provide a microscopic explanation for their thermodynamic properties. It strongly suggested that the Bekenstein-Hawking entropy wasn't just a mathematical analogy, but a real counting of the underlying quantum degrees of freedom, which string theory could identify as specific configurations of strings and branes. Hashtag tag outro.
It's just breathtaking when you step back and think about the journey physics has taken in pursuit of this unification. We started with Newton's absolute space and time,
which gave way to Einstein's dynamic warped spacetime.
Then fundamental particles were thought of as simple points,
which string theory replaces with tiny vibrating loops and filaments.
And our familiar 3 spatial dimensions.
Let's expand to 9, with 6 curled up into these intricate Calabi-Yau shapes dictating the laws of physics we see. It's a radical transformation of our fundamental picture of reality.
The mathematical elegance and the way it seems to tie so many loose ends together, particle families, force unification, gravity, black hole entropy, it's incredibly compelling. But the challenge remains, right? String theory offers this vast landscape of possibilities.
Tens of thousands, maybe 500 possible Calabi-Yau shapes, each leading to potentially different universes with different physical laws. The big question is, why our universe? Why this specific shape, these specific constants? We're still searching for what physicists call the principle of inevitability, the underlying reason why nature had to choose the specific vacuum state we live in. We haven't found that yet.
We need the theory to not just allow our universe, but to demand it in some sense.
Exactly. That's the ultimate goal.
And as we wrap up, string theory leaves us with this profound question about our origins. Conventional cosmology hits a wall at the Big Bang singularity, a point of infinite density, zero size, presumably the beginning of time itself.
But as we discussed with T-duality, string theory hints that this singularity might be an artifact of our older theories. The bound scenario suggests the universe might never have been infinitely small.
If the Big Bang wasn't a beginning from nothing, but rather a transition, a bounce from a previous state, what does that imply?
Well, it raises the absolutely mind-bending possibility, doesn't it? If the universe didn't begin at the Big Bang, does that mean it has a history before the Big Bang? Could time itself stretch back infinitely, or perhaps cyclically? It fundamentally challenges our concept of a starting point.
A universe without a definitive beginning. That's certainly food for thought. A reminder that this quest for the ultimate theory is really about understanding the deepest nature of existence itself.
It really is. The questions just keep getting bigger.
And on that note, that's our deep dive for today.